Okay, so last time, do you guys remember where did we stop at? Last time we were talking about conditional probability. And conditional probability is kind of an introduction to the probability analysis. Do you guys remember the rule? We have two events, A and B, and we are trying to find the probability of A given B already happened, what this is equal to. The probability of A intersection B over the probability of B. Okay, so this is kind of introduction to something called the total probability theory. So what is the total probability theory? Have anybody heard about this theory? Okay, so let's talk about this theory. Let's say that we have a bunch of events, and these events are mutually exclusive and collectively exhaustive. Let's say that we have event P1, event B2, B3, and a bunch of events up to Bn. So when I say these events are, and this is the sample space, so each one of these Bi, belongs to the sample space. I don't have any events out of the sample space. They all should be part of the sample space. So when I say these events are mutually exclusive, what does mean? Let's say that we are looking for the probability of event I intersection the probability of event J, where I and J belongs to the sample space. Both of them. So what is P intersection J? And they are all mutually exclusive. It's P, the null set. They don't have any intersection. So what is the union of from all the events, for all events I, what is the unions of all these events? Omega, all the sample space, right? I can write this from I equal to 1 to I equal to n, or all the events. Okay, so this is gonna give us the all sample space. That's what I mean by these events are mutually exclusive and collectively exhaustive. They don't have any intersection, and all of them, they make the whole sample space. Okay, so let's think these events are like, let's say that we are in California and we have a fault and we have different sources of earthquake. Each source of earthquake that can impact this building has nothing to do with each other. The source is a fault. The source is like a shaky soil. Each source has nothing to do with each other. Like the fault has nothing to do with the other source. So you have source 1, source 2, sources 3, up to sources n. Or same thing, you have a hurricane is coming to this building. And let's say, but the thing is, the hazards are dependent on each other. I was like thinking about hurricane, that you are gonna have damage from wind and the wind rainfall intrusion and storm surge and wave, but these hazards somehow dependent on each other. So this example can work, okay? All right, so let's think about the earthquake example. 3 earthquakes or 5 earthquakes that has nothing to do with each other is gonna impact the building and it's gonna cause damage. The damage is gonna be something like this. Let's say that the damage is A, okay? So A is like a damage is gonna happen to your building. Part of it is gonna come from source 1, B1, and part of it is gonna come from source 2, source 3, source n. You guys understand this? So damage is gonna happen, and bunch of sources are gonna be part of this damage, not only one source, okay? Some sources gonna have more contribution, and some sources gonna have less contribution, okay? Depends on the source characteristics, all right? So let's revise what is gonna happen. Or actually you can think about it like the other way. Like if you don't understand it that way, let's say that you having a damage to your building A, but you don't know where this damage came from. So part of this damage came from event A, part of this damage come from event B, event C, and here is like event B1, B2, B3, up to Bn. And each one of these sources is causing this damage, not only one source. All right, so let's see how we can use the conditional probability theory to help us with the total probability theory. The thing is, I want to find out what is the probability of A. That's what I want to find out, the probability of A. So the probability of A, if we think about it, is the probability of P1 intersection A and the probability of P2 intersection A, P3 intersection A. Once you find the intersection with all the events, you are going to find them piece by piece. You're going to find this piece and then the next piece and the next piece until you find all of them. So this is going to be probability of A intersection B1 plus the probability of A intersection B2 plus the probability of A intersection Bn. But look at this, the total probability theory. The total probability theory, I can say that the probability of A intersection B is equal to the probability of A conditioned on B multiplied the probability of B. So I can substitute with this here. So I can say that this is equal to the probability of A conditioned on B1 multiplied by the probability of B1 plus the probability of A conditioned on B2 multiplied by the probability of B2 plus until I go to the probability of A conditioned on Bi or Bn, the last one, multiplied by the probability of Bn. So I can say at the end, if you want to find the probability of damage, Ba is going to be equal to the summation from I equal to 1 up to n of the probability of A conditioned on Bi multiplied by the probability of Bi. That is the total probability theory. You guys got that? So, you know right now, if a damage happened to a specific building from multiple sources, you need to find the probability of damage given source 1 multiplied by the probability of source 1 plus the probability of damage coming from source 2 multiplied by the probability of source 2. If the probability of a specific source is 0, what is the probability of damage that you are going to get from this source? 0, right? Because if this source didn't happen already, so definitely there is no damage from this source. All right, so let's link this with the probability concept. So actually, we already said that. I'm just gonna write the equation that I have here. So for a building, if you wanna find the probability of a specific damage state to happen, that's actually what we do. We say the probability of the damage state given that intensity measure equal to X multiplied by the probability of this intensity measure. For example, let's say flooding. If a flooding is going to happen, it's going to damage my building. I need to find the probability of damage coming from flood depths equal to 2 meters multiplied by the probability of flood depths of 2 meters to happen, right? Like I need to find out what is the probability of getting flood depths of 2 meters. Then I multiply it by the probability of damage that is going to happen if this event happened already, okay? All right, so let's have an example, and it's going to be on earthquake. So say in simple, seismic risk assessment, a building is exposed to earthquake hazard from 3 different sources. So let's say I have my building here, and this is source 1, which is a fault, source number 1. This fault can cause an earthquake, and there's another source, it's not a fault. So when you know the location of the fault, so that's basically an exact source of hazard. Sometimes you don't know what is the exact location of the source. So basically, rather than saying it's a line, it's a specific area, and somehow in this area can cause earthquake, and then this building is gonna be impacted. And this is source number 3. So I have source number 2, source number 3, and each source at a distance from my building. Let's say this is R1, R2, R3. And I give you the probability of damage that is gonna happen to this building if source 1 already happened is gonna be equal to 0.9. That means source number 1 is really damageable. Like if this fault shaped, the probability of having damage is 90%. The probability of damage given that source 2 happened is 0.6. The probability of damage given source 3 already happened is 0.1. So that means that source 3 is not that bad. I mean, like, if it happens, it's not gonna cause that much damage. All right, so this damage, given that the source happened, but let's just see, what is the probability of the earthquake to happen, or this source to generate seismic hazard? The probability of source 1 to happen is very small, is 0.1. The probability of source 2 is 0.3. The probability of source 3 is equal to 0.4. So what I'm asking for here, knowing that source 1, 2, and 3 are mutually exclusive, determine the probability that a building will be damaged next year. By the way, all these probability is the probability of a fault to generate an earthquake in the coming year. So these, the probability of a fault to generate an earthquake in the coming year. And I'm asking you to find out, determine the probability of the probability that a building will be damaged next year. Okay, I want to find the probability of damage. We are going to use what? We're going to use what we learned here. If you want to find the probability of damage, you want to multiply the probability of damage given source 1 by the probability of source 1 plus the probability of damage given that source 2. So this by this plus this by this plus this by this. But look at this. I said to apply this rule, the events have to be mutually exclusive and collectively exhaustive. So here it's stated clearly that knowing that event 1, 2, and 3 are mutually exclusive, so that's given. But we need to make sure that they are collectively exhaustive. Do you guys know how to know if they are collectively exhaustive or not?
Summation of the probability.
We need to sum all of them. 0.1 plus 0.3 is gonna be 0.4 plus 0.4 is gonna be 0.8. That means there is another 20% that we don't know. But since we are not given any other thing, that means like the other 20% are 0. Like what is the probability if there is no earthquake? So like I can say here, the probability of damage given that there is no earthquake. All right, so we're gonna talk about it in a little bit, but we can move forward with this, using this rule. All right, so let's do this. The probability of damage is gonna be equal to the summation of the probability of damage given event, let's say, EI, multiplied by the probability of the event EI from I equal to 1 up to I equal to n. All right. So basically, if you want to expand this rule, and I know that you all can do it, it's going to be the probability of the given I multiplied by the probability of I plus the probability of the given event 2I plus the probability of the given event number 3 multiplied by the probability of event number 3. And if you want to get the other so that you can make it mutually exclusive, you can keep it like this. But if you want to put the other event, you can do it or you cannot do it, it's fine. The probability of damage given none of these events to happen multiplied by the probability of no event to happen. Okay? The probability of no event to happen is 20%, right? The rest of this no event is going to be 0.2%. And the probability of damage if there is no event is 0, right? You will not get damage from if there's earthquake happens. So I know that this is for sure 0. So if this is 0.2 multiplied by 0, all this term is going to be 0. So now I can find out the probability of damage. The probability of damage is going to be, you guys tell me, what should I write? 0.9 multiplied by 0.1 plus
0.6
0.6 plus
0.1 0.4
plus 0 multiplied by 0.2. And when you finish this, you're going to find out that this is equal to 0.31. That is the probability of having damage from all the sources. Okay, I just want to mention something about these hazards. All right, I'm going to ask you a question. Where do we get a probability of damage given an event to happen? We get this from structure analysis, from fragility. If you want to know, that's actually what we do when we do structure analysis, right? We put an earthquake in a building and see which joint is going to be damaged, which beams is going to be damaged. So to know damage, giving a load happen, that's a structure analysis problem. So that's our job. But the probability of a hazard to happen, that needs a seismologist to find out what is the probability of an earthquake to happen in San Andreas Fault in California. So that's seismologists need to give us this information. So let's put this here. Like, yeah, so it's like the same thing when we talk about fragility. Fragility is hazard intensity, like let's say hazard I or event I, and here's the probability of damage. And it's a curve, something like this. So you want to say if intensity is its hazard I, that is the probability of damage. So what is the probability of damage conditioned on hazard I? Let's say this is the hazard. What is the probability of hazard number 2? What is the probability of the hazard number 3? So let's say, for example, this is 0.9, this is 0.6, this is 0.1. Same thing if you are thinking about flooding. Like if you are thinking about flooding, what's the probability of damage given a flood depth 2 meters? It's going to be this, 1 meter, 0.5 meter. So we get this from fragility analysis. We get this from, as I said, seismologists or people, hydrologists that give us 100-year hazard map, 200-year hazard map. So think about this. Other than having different sources, you can have different return periods. Like hydrologists are going to develop us a 1,000-year hazard map, and a 500-year hazard map, and a 100-year hazard map. Okay. So same thing. Like there's hazard curves. You guys who has been with me in the course from last semester, do you guys remember when we used the ASCE tool for seismic? There's a website that we entered, and we start entering the values of the location of the area, the seismic coefficient. There's a hazard tool, like something like this. It tells you a 10,000-year event, a 1,000-year event, a 500-year event. Think about it. It's like event number 1, 2, or 3, okay? And if you wanna find out a hazard intensity coming from these 3 sources, like let's say I'm looking for a spectral acceleration of 1g. So spectral acceleration of 1g can happen for these different sources, but what is the one that is more likely to happen? Okay, there's other sources that can give you the 1g more than, like, with more probability than the other ones, because the other one is very far away. So let's see, like here, I have I is 0.1, this is 0.3, and this is 0.4. Okay, so think about it as a different sources, or think about it as a different return periods that you are looking at. If the return period is, if we are saying that a 10,000 return period, it has low probability to happen, but if 100-year return period, that has a high probability than the 1,000, okay? Right, because a 10,000-year event, that's something like is not gonna happen in our ages, or even like it's gonna take a long time to happen. That's an event that is gonna kill a lot of people. But a 100-year event, it's a very close event. 10-year event, that's much more closer, that has much higher probability to happen. So that's why this has much higher probability to happen. But look at this. Since this has much higher probability to happen, but has low damage. Okay? This one has, like, this is a much more damageable event. If it happens, 90% probability of getting damaged, but it has low probability to happen. Okay? All right, we're gonna get to this through a theory. It's called Bayes' theory. Bayes' theory. So what is Bayes' theory? It's like similar to this one. It says same assumptions. If you have events BI are mutually exclusive and collectively exhausted, define the sample space. Okay, B1 up to Bn. And A is an arbitrary event also defined within the sample space. So you have an event that happened within the sample space. So what the thing is, rather than I want to find the probability of A, which is the probability of damage, okay, I want to find what is the probability of hazard intensity 1 given that a specific level of damage happened. Okay, so I mean, like, if I came to a building and I already found the damage, like it's already damaged, I want to find out what is the probability of source 1 to cause this damage, and source 2 to cause this damage, and source 3 to cause this damage. Okay, but what happened here, I said, what is the probability of damage given that this source already happened? It's kind of the opposite thing. Rather than I want to find what we did before, is probability of A given B, or the probability of damage given source 1. What I want to find out right now, what is the probability of source 1 given that the damage already happened? Okay, so it's kind of an opposite thing, but we're gonna find out. It is the same thing. I'm gonna draw the same shape. I have my sample space. I have my mutually exclusive, collectively exhausted events, and I have an arbitrary event, which is the damage. And I have, this is BI, sorry, B1, B2, B3 up to Bn, okay? All right, so if you want to find out the probability of a intersection event BI, using the conditional probability, what do you guys can tell about this? If I want to find A intersection BI or B1, if I want to find this one, it is the probability of A, conditioned on BI multiplied by the probability of BI, right? Or it is the probability of BI conditioned on A multiplied by
A.
the probability of A, right? This is the same thing. If you guys don't understand this, you can say the probability of A given BI is gonna be equal to the probability of A intersection BI over the probability of BI. And same thing, the probability of BI conditioned on A is gonna also be equal to the probability of A intersection BI over the probability of A. So you have, these terms are equal to each other, so this multiplied by this is gonna be equal to this multiplied by this, right? Okay, so what I'm interested in right now, this term, the probability of BI, specific hazard, given that amount of damage happened. Okay, so I'm interested in the probability of BI given that A already happened. So this is gonna be equal to the probability of A intersection BI over BA. So let's find out how we can find this. The thing is, I already knew that the probability of A intersection BI is equal to this part, right? Is equal to the probability of A conditioned on BI multiplied by the probability of BI. And all this is divided by the probability of A. Is that right? BI given A. And actually, I can also substitute with A. Like A, I can leave it that way, or I can write it that way. I'm gonna keep it the same. The probability of A given BI already happened. And actually, we have here the probability of A is equal to the summation from I equal to 1 up to n. The probability of A given BI multiplied the probability of BI. And here, I have the BI. So, let me write it here. So right now, a probability of earthquake BI, given that a specific amount of damage already happened, is gonna be equal to the probability of A given BI, and I'm gonna put here the summation from I equal to 1 up to n, the probability of A given BI multiplied by the probability of BI, and here is the probability of BI. Let me ask you a question. Can I slash this with this?
No.
Why?
Because
This is an inside summation, right? I can't do this. So this has to be here, and this has to be same like this. So this is a really, really interesting formula. Why? And that's actually a very, very important formula in the reliability, engineering reliability. Why? We call this term prior, and we call this term posterior, and we call this term likelihood. What does that mean? That's interesting. Why? Okay, so let's say you know the probability of a specific event, natural hazard event, to happen, okay? And what are you looking for? What is the probability of this event given a specific damage already happened? That's completely different quantities, okay? All right, so to know this, you use a bunch of information about this event. A lot of information about this event. So you have an input and you use some probability information and then use this function to find what is gonna give you next, okay? It's like a machine learning. You give the machine learning some information and some likelihood and come up with what is the probability of something to happen given other things to happen, okay? All right, so let's actually use this in this problem. How? I give you the probability of damage given that earthquake number 1 happened, and the probability of damage given earthquake 2 that happened. What I want to find right now, what is the probability of earthquake 1 given damage already happened? Okay? Here, damage didn't happen. I want to find the probability of damage given this happened. Okay, and I want to find out what is the probability of earthquake 2 given that damage already happened, and the probability of earthquake 3 given that the damage already happened. So, what is this is going to be equal to? All right, what is the probability of damage given event 1? It's already given, right? 0.9. So I already give you this, 0.9. What is this? This actually is the probability, it's PA. And that's what we were trying to find here, right? We multiplied all this together so that we can find the probability of the damage, or the probability of A. And we find this is equal to 0.31. So here this is equal to 0.31. What is the probability of earthquake 1? It's already given here, it's 0.1. So same thing, but this is for event number 2. Event number 2, we have 0.6 over 0.31. And here I'm gonna multiply by 0.3. And here is gonna be this 0.1 multiplied by 0.31. And here I'm gonna multiply by the probability of event 3, which is 0.4. Does anybody got lost in this math? By the way, it's all systematic. Maybe you got lost, so we can't catch you back. Right, so right now I'm trying to find the reverse of this. The probability of earthquake event 1, given that damage already happened. This quantity is the probability of the damage given the event happened. Okay, so the earthquake already happened, but this one, the earthquake didn't happen. I want to find the probability of this event to happen, given that I already know the damage. Okay, so it's like kind of opposite. Okay, so this function is going to tell us how you need to find what is the probability of damage happen from source, given that this source already happened, and multiplied by the probability of the damage, which we got it here, 0.31, and then multiplied by the probability of the source. We did this for the 3 of them, and this is going to be equal to this is going to be equal to 0.29, and this is going to be equal to 0.58, and this is going to be equal to 0.13. Let me ask you a question. This one is the lowest, 0.13, even that the probability of this hazard to happen is the highest. Like the probability of this hazard to happen. So let's think about it. By the way, before I forgot this process, when I try to find the probability of I and the probability of hazard 1, hazard 2, hazard 3, it's called hazard risk deaggregation analysis. Risk. And by the way, you can go to Google Scholar and search risk deaggregation analysis and natural hazards. You will find a lot of paper using this application to identify what is the sources of damage that can cause damage to buildings. You have source 1, source 2, source 3. So, as we can see in this example, most of the damage came from zone 2, because the probability of seismic or earthquake number 2, given the damage already happened, is 0.58, which is the highest level. So that source has much higher probability to cause damage. Okay, why? Even that this source is 0.9%, like the probability of damage, if the probability of damage having given that source already happened is 0.9%, but who knows if this source happened or not. If it happened, but the thing is it has low probability to happen. So when you multiply them together, this number is gonna get down. Even that this source, if it happened, is gonna destroy the whole area. But what is the probability of this happening? Is 0.1. This source has low damageability, like the probability of damage of this source to having given that seismic 3 happen is 10%, but it was 0.4%, has much higher probability, but it still is not like this one. This one has a median, and median, when we multiply them together, it gives you a little bit bigger number, okay? Even it has like a medium damage given it's happened, but it has much higher probability than this one, okay? So that's actually how you think about it intuitively. But if it comes to rules, what is the most important rules that we learned today? The conditional probability rule, the total probability theory. Where's the total probability theory? This one. This is the second rule. The third rule is the Bayes theory, this one, okay? So I'm gonna give you a bunch of numbers in the exam, and you're gonna use these numbers to try to fit it here. If I told you what is the probability of a specific damage given that an earthquake happened, so don't mix them up. Don't say that this 0.9 is the probability of I given D. So try to figure out which one you should fit in, okay? Does anybody have any questions so far? So let's shift to the next topic. We're gonna talk about random variables.
How did you get a sigma in the denominator?
A what?
How did you get a sigma?
This one?
Yeah.
This is the probability of A, the probability of damage, and it's equal to the summation of all the events, and that's what we do in the first problem that we solved. Do you remember when I give you the problem? I give you all these numbers, and then we start doing this, and that's the probability of A. So that's the first part that we solved. This is kind of like the second part of the problem. So, but if I ask you right away on this, you have to do all this first, and then you jump back. So solving the entire problem, it's all this four. This is part one, and this is part two. Okay? And if you want to do it again, so all what you have to do, the probability of A is going to be equal to, you take it 1 by 1, 0.9 multiplied by 0.1 plus 0.6 multiplied by 0.3 plus 0.1 multiplied by 0.4, and then you find this number here. So that's the probability of A, the summation of the conditional probability by the absolute probability. This by this plus this by this plus this by this. Okay. All right, so let's So right now we finished the part that includes the statistics and mostly and a little bit of probability. The concept of random variables. Alright, so the concept of random variables, anything that is uncertain, it's called random variable. Do you guys remember in the first lecture when I drew a simple beam like this and I told you the thing is, it was kind of not real when you solve the structure analysis problem and I give you a load of 10 because there's nothing is certain and everything is uncertain, and this 10 should have mu and sigma, mean and standard deviation. So since any parameter has a mean and a standard deviation, that means it's a random variable. So this load is a random variable, these reactions is a random variable, the bending moment here is a random variable, all these are random variables. So random variable, example of random variables, so structural engineering has events that also involving engineering parameters that most of them are random variables. The concrete compressive strength, random variable. The steel yield strength is a random variable. Same thing if you are talking about wind speed. So usually when we say what is, if I have a wind speed V is less than or equal to a specific value, let's say what is the probability of having a wind speed V less than 30 miles per hour. This is a random variable. RV, random variable. And we usually put them in these parentheses. What is the F yield of a steel to be more than A and less than B? Like F yield is less than a number and bigger than number, F yield is a random variable. Spectral acceleration to be less than 2g, spectral acceleration is a random variable because it's uncertain. So the definition of a random variable is that a variable that can be assumed any number of values and the precise value of this value is uncertain or unpredictable, but it can be characterized by statistical regulations like a normal distribution, a log normal distribution. So that's why we use mean and standard deviation to describe them because they are random. There's no way that we can say that this is a specific number. If something has a specific number, we call it a deterministic value. There's no way. If I have $10 in my pocket, it's then $10. There's no way it's gonna be 11. There's no way it's gonna be 9. Okay, so that's a deterministic value. But if I didn't tell you how much money I have in my pocket, you will not know. It's a random variable to you, but it's deterministic to me. So you will tell me, okay, maybe you will have, because your pocket is not that big, it's definitely not a $10,000. Because if $10 is gonna be big, so you will gonna use your intuition, so you are gonna make that processing and use your intuition to make a suggestion about how much money that I have in my pocket. So it's a random variable to you. So it will tell me, maybe you have around 100, 200, that's uncertain, that's unpredictable. So that's a random variable. Same thing, my load on this beam, nobody knows my exact weight, but you can give me a range. Actually, I think average, you are like 180 pounds, 200 pounds. So that's a random variable to you. When it's gonna be deterministic? When I put myself on a weight that is gonna give me my exact weight. So that's the difference between random variable and deterministic variables. So random variables still follow the probability concept. That is, I need an experiment and I need an outcomes and I need some events so that I can do some probability assignment. So if you want to know the compressive strength of a concrete, I told you it's a random variable. I have to take some samples and do an experiment and test these samples and have a bunch of outcomes of the compressive strength and then try to find what is the probability of having a compressive strength of 25 Newton per millimeter square or something, okay? All right, so random variables has two types. The first type is called discrete random variable and continuous random variable. So what is the discrete and continuous random variable? Discrete, that means you have a limited number, accountable number of outcomes. You take a compressive strength of a concrete, or you have steel coupons and you are trying to find the F yield of these coupons, or any measures that are countable. But if you have an infinite number of samples, that is a continuous random variable. Okay, so let's first talk about the discrete random variables. Number one, discrete random variables. So for discrete random variables, usually you try to find what is the frequency of the variable. So let's say that I have a variable x, and this variable, I start to put how many of them are equal to, for example, a specific number, and another number, another number, another number, and try to find what are their frequencies. Like, let's say we are trying to collect the age of the people here, so, and then we are trying to find, maybe you will find, I don't know, 5 people are the same age, 3 people are the same age, like let's say age of 28, and some people are the same age of 30, some people are the same age of 20. So I try to find the frequency. But if you want to like put this in something called probability mass distribution, what's that mean? If you want to find out what is the probability of somebody here in this class has an age of an XI, like maybe 28 years old or 26 years old. This. Sometimes we can write this, what is the probability of a random variable, x is the random variable, to be equal to a specific number. So the x capital is the random variable that I don't know. And the x small is the value assigned to the random variable. What is the probability of the age of somebody in this class to be like 30 years old? Or what is the probability of the height of somebody in this class is 6 foot? Or what is the probability of a wind speed to be equal to 100 miles per hour? So if I want to write it, so it's gonna be V equal to 100 miles per hour. So usually that's the random number, and this is the assigned value to the random number. We can write it as the probability of the random number, and in between parentheses, I can put xi, the value. Or I can write it this way, f, and x capital, and here's xi. All these means what is the probability of a random variable x is equal to this one. So that's how you read this equation. And the sum of all the probabilities all xi's should be equal to 1. Okay, let's say write it right here. I'm gonna look at the wind speed. And here is fx of x. And I'm looking at wind speed, maybe x1, let's say 50 miles per hour, 75 miles per hour, 100, 124, 125, 150, x1, x2, x3. And the probability of having 100 miles per hour is that high. The probability of having 75 is that high. And the probability of 50, here's the 125, and here's the 150. So since I was able to represent them by discrete values, that's called discrete random variable. And each value, this is gonna give me B1, and this is gonna give me B2, B3, B4, and B5. And all of these are the sample space. Like all these numbers, I only have x1, x2, x5. If you sum all these probabilities, should give you the 100% probability. Okay, if you sum B1 plus B2 plus B3 up to B5, it's gonna give you the 100% probability, because that's what constructs the entire sample space. So we call this probability mass function. Probability mass function, PMF. PMF, probability mass function. Okay, let's say I want to find out the cumulative of all these. The cumulative of all these, we write it F capital, Fx of x. This is probability and this is cumulative probability, okay? This is probability and this is cumulative probability. And here I have my variable x. So what I do in the cumulative probability, basically at x1, so x1, this is the probability, and then you sum the probability of the next one, and the probability of the next one, and the probability of the next one, until you go back to the other one. So here you have B1, here is B1 plus B2, and so on. And at the end, it should be, what is the value here?
One.
One. It's the total probability, all the steps. All right, we call this cumulative distribution function. Let me write them here so that again, this is probability mass function. And this is or CGN. Okay? All right. And if you want to find the probability of a specific random variable of interest, other than these, you just like come here and cross these lines, and this is going to be xi that you are looking at. You can find the probability, or you can find the cumulative probability. Okay, this is the cumulative probability. When you find, if you want to find up to xi, like if you are going to write it, one second, I don't have it here. I don't have it, but if you want to find it, you sum all of them until you stop at xi, not all xi. If you sum all xi, it's going to give you 1. But if you want to find the cumulative probability at xi, you sum until you come here, and this is the cumulative probability. Okay? All right, so I'm going to write them here. So in the discrete, maybe I will write them here. Just like, it's like rather than writing B, I told you that we can write f small x of a random variable xi is the same like the probability of x equal to xi. So rather than I can write it that way, I can write it that way. That's called probability, not cumulative probability, okay? Cumulative that you have to sum all the probability before the variable. And the cumulative probability is the f capital Fx of xi, and this is the probability of x to be less than or equal to xi. Okay? Less than or equal. Do you guys get it? So you have to find the probability of all these, the less than or equal. But the f is small is just the value at this point. What is the value at this point? Okay? So this is equal and this is less than or equal. And if you find yeah, right here something is called if I'm trying to find the limit when x at infinity, the fx of xi is going to be equal to 1. When x goes to the infinity, this is going to be equal to 1. But I think this is somehow close to the concept of the continuous random variable, but it applies here too. So we're going to use this in a few minutes. Or you can write this, what is the probability when x is less than or equal to infinity, that is also equal to 1. Because x is going to be always less than infinity, so it's going to be in the entire sample space. All these sample space. Okay, so we are going to understand this more when we talk right now about the continuous random variables. Number 2, continuous random variables, which is most of our application. So we rarely will have discrete random variables. So it's going to be something like this. and I have, that's a continuous random variable, rather than being as a single points, is gonna be continuous. It has a continuous function, not a discrete or disruptive function. So what is about this function? So if you have two random variables, A, or one random variable, but I wanna find the probability at A and B. Or what is the probability of my random variable to be here, in between A and B? So let's find out. Okay, let me ask you, what is the area under the curve? What is the value of the area under the curve if I integrated all the possible outcomes? It's gonna be 1, okay? Because the area under this curve should be 1, because that's all the possible outcomes that you are gonna have, okay? I have to integrate from negative infinity to positive infinity. It's gonna give me 1, okay? All right, so let me explain it, okay? I'm gonna write here something that's called the probability axiom. All right, the probability of any random variable or any continuous random variable should be in between 0 and 1, right? That's what we learned. Should not, it's not gonna be negative, it's not gonna be more than 1. And the integration from negative infinity to positive infinity of the probability of this random variable is gonna be equal to 1, okay? Because I've integrated this is all the possible outcomes. So the integration of this should be equal to 1. And if A is less than B, like this example, and I want to find the probability of B, or let's not say the probability of B, we either say B, X, B, and this means the probability of X less than or equal B. Now if I want to find this is going to be equal to, if you want to find what is the probability of my random variable to less than B, it's going to be equal to this part and this part, right? So this is going to be equal to the probability of X less than or equal A plus, let me write it down here. Less than or equal A plus the probability of X more than A and less than or equal B, right? So this is the probability of X is less than A, is more than A and less than B, plus the probability of all the events that are less than A. But let's find this. What is the probability of X that is more than A and less than B? So that is going to be equal to the probability of everything that is less than B minus the probability of everything less than A. So that's the probability of X less than B minus the probability of X less than A. Is that right? So if you want to find out what is the probability of a random variable to be in this zone, so this is going to be equal to all this minus all this. Like all this part from here to here minus this part is going to give you the bar under the curve. And we can write it that way. We can write this as fxb minus fxa, because fx is the cumulative probability. So fxa is the probability of x less than a. fxb is the probability of x less than b. this thing is gonna have a little bit of mass, so I have, this is my distribution. If you want to find out the probability at a specific number, like here, you want to find the value of f x at x here. So let's find out how we can find it. Actually, to do this, it's still the area under the curve under this point. But the thing is, if you did it that way, this area of this line is 0. But the thing is, to do it, we do it that way. Like, it's basically this interval, which is this small interval, like from here to here. And if we take it out, it's gonna be showing like something like this. And this area is very, very small, dx, very infinitesimal area. And the value here is a little bit different than the value here. So the value here is like let's say, did you see this part? A and B? Let's say that this is A and this is B. But the distance between them is not that big. It's very small, okay? So here is F. So A and B, I'm gonna name it differently. I'm gonna name it X and X plus delta X. So if you wanna find out what is the Fx, this is a small thing, so you need to find what is the cumulative distribution, Fx at x, and what is at Fx plus delta x. Is that right? Okay, so if I'm trying to find what is Fx of the random variable x, you are gonna get all this part, right? And if you wanna try to find the 1 plus delta x, you are gonna take delta x and try to find the area. If you subtract them from each other, it's gonna give you the value Fx at this small interval, okay? Even it's a very small, but this is how we find it. But the way that we write it mathematically, we write it that way. If you wanna find what is the probability, F small is the probability, F capital is the cumulative probability. Probability, that means at a single point. What is the probability here? Which is this part. And if it's here, so at this single point. F capital is the cumulative. You have to sum all the probability behind this point. Okay, let's focus on the probability, not the cumulative probability. I want to find Fx at a random variable x. Actually, this is equal to the limit when delta x is equal to 0, like when this delta x is very, very small, is approaching to 0. And you try to find the probability of your random variable x to be more than x and less than x plus delta x over delta x. So here's what I'm trying to do. I'm trying to find what is the probability of my random variable to be in between this small interval, between x and delta x. This is the definition of differentiation. If you guys go back to the math basics, the definition of differentiation is the limit when delta x is equal to 0. That's how the differentiation came from. So basically, we can write this in a different way. The limit delta x is approaching to 0, Fx, put it, plus delta x. Let me write it the whole line so I can have space here. This is gonna be the limit when delta x approaching to 0. And this part, I can write it like this part. I can write it as f x at x plus delta x minus fx at x over delta x. F here minus f here, so I subtract them together. And this is the definition of the differentiation d dx of the function fx. If you go back and write on Google, what is the definition of differentiation? This is gonna show up. It is the limit when delta x is equal to 0 of your function after delta x minus the function at x itself. How your function got different when you moved delta x. So that's the definition of differentiation. So if you want to find out the value of the probability of a random variable x at a specific value, you differentiate the cumulative distribution function fx at that random variable. Okay? And the opposite. If you have the cumulative probability fx at a random variable x, you can integrate this function from x equal to 0 up to the x that you want to have. And that makes sense. If I want to find the cumulative probability here at a, I do integration from 0 until the random variable x. So if my x is here, I integrate from negative infinity. Sorry, this should be negative infinity, not 0. So I integrate from the negative infinity until I stop at my variable. Okay, so
I have a question.
sure.
In the first fx you written p of x, it includes,
This?
yes, x less than or equal to capital X. So it includes the left hand interval, whereas on the left hand side, at the bottom,
Here?
yeah, p of a, it does not include the left hand interval. It's
The probability, this
greater-
one?
Yes.
This one include all this part, minus this part, it's gonna give you this part. This minus this, fxb minus fxa is gonna give you the area under this curve. So I wanna do the same here, so I have x and delta x, so I subtract fx, deal with it as a b, and deal with this as an a.
I understand that, but on the left hand side, you have excluded the point at the interval.
Oh, you are saying this one?
Yes, you have excluded.
Because I
it's
already
not
have it
equal-
here.
Yes, you don't have it equal to a,
Hmm.
but on the equation, you included the interval, the point at the interval. You're trying to understand what I'm saying?
Mm-hmm. So.
There's an equal to, basically, on the right hand equation, where you written fx, and the left one, you just excluded the interval.
You mean like this part?
Yeah, so I was just trying to. You don't have an equal to here, but you have an equal to here.
Oh, okay, so let me double check. Yeah, there's no equal. Sorry. It's in the notes, right? All right, so if I integrated this part, here with dx is gonna give me the cumulative distribution function. But the thing is, since I already have x as the boundary of the integration, we can change the name of this variable. Like I can make it any name, so that the thing is, after I integrate it, I'm gonna put x again. So maybe we are gonna put xc, I'm gonna put xc here. So once I integrate this function, it's gonna be function in xc. When I substitute with x, it's gonna be function in x again. All right, so you don't mix things up. If you wanna keep it x, you can keep it x. The thing is, so that you don't get confused, once you integrate the whole function, is gonna be function in xc squared, and then you substitute with x, you're gonna remove hxc and put x. So it's gonna be the same thing. So usually we change, since everything is gonna be, this is not a number, x, I didn't give it to you as 10. If I give it to you as a 10, you can keep this as an x. But right now, everything is variable. So I kept them xc, so when you substitute with x, it's gonna return back to the same thing. Okay, let's put this graphically, how this look like. Let's say that we have random variable x, and this is the, by the way, we call this, if you guys remember, we call this as probability mass function. The opposite one in the continuous random variable, we call it probability density function. Density function, or BDF. So I'm gonna write a BDF here. And also a CDF, cumulative distribution function. So this is, CDF is gonna be F capital. Let's say, and this one, the blue is not working anymore. Can you guys see the blue?
No.
And this is the cumulative distribution function. Something like this. You guys tell me, what is the value here? It's 1, right? That's the maximum value. Once you sum all these values together, you are gonna get, rather than having steps, you are gonna have a continuous function, and it reaches to 1. Alright. So if I pick two values, A and B, here, so the fx of any random variable should be more than 0 and less than or equal 1. You guys tell me, what is the fx at infinity? 1, right? That's here, infinity, and that's the value is equal to 1. And what is the probability of x more than a and less than or equal b? How can I get it? It is the area under this curve, right? The one that I put it here. So if you want to find it, you are going to find what is the fx at b minus the fx at a, right? You want to find all the area at b minus all the area at a. You are going to give this little area, or you can come directly to this curve. This curve is going to give you here fx at a, and this one is going to give you fx at b. If you subtract them from each other, you are going to get the probability of x is more than a and less than b. All right, I know I threw a lot of probability stuff today, but this is how the course is going to be. I mean, like at least this part. So you need to keep up with everything that you're thinking. So let's focus what we got today. It's like, or maybe the entire course. What is the most important till now? The conditional probability, the total probability theory. Number 3 is the Bayes theory. That's number 3. Number 4 is the random variables. That's the 4 things that we have done today. Go focus on them, try to see what we have done, because you need to understand this, because next time we're gonna build on this. We're gonna take something called the joint probability. If you have 2 events, what is the probability of event A and event B to happen together? What is their joint probability? What is the marginal probability? So it's gonna be like a 3D. Can you see this curve? This curve is like you only have an event X. What is this? There's another event in the other dimension Y is gonna happen. So rather than having a curve, it's gonna be a surface. Okay? So you need to be on top of the game. So try to go study this so that on Thursday we can have to continue this, right? See you guys next week. Next